In the beginning, there was nothing. Or so we thought. But even in the deepest emptiness, even in the darkest void between the stars, something stirs. The vacuum hums with invisible energy. Fields ripple through every corner of existence. And particles, those tiny messengers of reality, flicker in and out of being like fireflies in an endless night. This is the story of quantum fields, the invisible ocean that fills the universe, the fabric from which everything you see, everything you touch, everything you are, is woven. It is a story that reaches from the smallest distances imaginable, smaller than atoms, smaller than protons, down to scales where space and time themselves begin to dissolve, all the way up to the vast cosmic web, the structure of galaxies scattered across billions of light years. It is a story of symmetry and its breaking, of particles that are really waves, of forces that emerge from the geometry of invisible dimensions. It is a story written in the language of mathematics but painted in the colors of wonder. So take a breath. Let your mind settle. And prepare to journey into the quantum realm, where the impossible becomes routine, where the vacuum is alive, and where the deepest secrets of nature wait in the stillness, ready to be discovered. In the deepest stillness of space, far beyond the reach of our eyes, beyond the glow of distant stars and the sweep of spiral galaxies, there exists something extraordinary. It is not a thing you can touch or see, not a planet or a comet streaking through the dark. It is something far stranger, far more fundamental. It is the fabric from which everything is woven, the invisible ocean in which all of reality swims. Scientists call it a quantum field, and it fills every corner of the universe, from the emptiest void between galaxies to the space between your fingers, to the tiny gaps inside every atom in your body. In the deepest stillness of space, far beyond the reach of our eyes, beyond the glow of distant stars and the sweep of spiral galaxies, there exists something extraordinary. It is not a thing you can touch or see, not a planet or a comet streaking through the dark. It is something far stranger, far more fundamental. It is the fabric from which everything is woven, the invisible ocean in which all of reality swims. Scientists call it a quantum field, and it fills every corner of the universe, from the emptiest void between galaxies to the space between your fingers, to the tiny gaps inside every atom in your body. Imagine standing on a beach at twilight, watching the ocean stretch endlessly before you. The water is calm, but if you look closely, you see tiny ripples, gentle waves rising and falling in rhythm. Now imagine that the entire universe is like that ocean, but instead of water, it is made of fields, invisible fields of energy that stretch through all of space and all of time. Each type of particle that exists, each electron spinning around an atom, each quark nestled inside a proton, is not really a separate little ball. Instead, it is a ripple, a wave, an excitation in its own special field. The electron is a ripple in the electron field. The quark is a ripple in the quark field. And these fields are everywhere, always, filling the cosmos completely. This idea, this beautiful and strange idea, comes from quantum field theory, a way of understanding the universe that combines two of the most important discoveries in physics. The first is quantum mechanics, the science of the very small, the realm where particles behave in ways that seem impossible, where they can be in two places at once, where they flicker with uncertainty. The second is special relativity, Einstein's insight that space and time are woven together, that nothing can travel faster than light, that energy and mass are two faces of the same coin. When you bring these two ideas together, when you let them dance and intertwine, you get quantum field theory, a framework that describes not just particles, but the fields that give birth to them. And here is where it becomes even stranger, even more wonderful. These fields, these invisible oceans of energy, are never truly still. Even when a field is in its lowest energy state, even when it seems as calm as it could possibly be, it is not quiet. It trembles. It vibrates with tiny, restless fluctuations. Physicists call this the zero-point energy, the energy that remains even at absolute zero, even in the deepest cold, even in the darkest emptiness. The quantum vacuum, the space we think of as empty, is not empty at all. It is alive with motion, a seething, frothing sea of activity. In this strange quantum vacuum, something remarkable happens all the time, in every cubic inch of space, in every fleeting moment. Pairs of particles suddenly appear out of nowhere, a particle and its opposite, its antiparticle, blinking into existence like sparks in the dark. They are called virtual particles, and they live for only the briefest instant before they find each other again and vanish, annihilating in a flash of energy. This happens constantly, everywhere, a cosmic dance of creation and destruction playing out in the space around you, in the space inside you, in the emptiness between stars. The vacuum hums with this hidden life, invisible but real, a reminder that nothing in the universe is ever truly still. And this is one of the great gifts of quantum field theory. Unlike the older version of quantum mechanics, which could describe how particles move and interact but could not explain where they come from or where they go, quantum field theory allows particles to be born and to die. A field can ripple into a particle. A particle can smooth back into the field. Creation and destruction are woven into the very fabric of reality. The universe is not a collection of unchanging pieces. It is a living tapestry, constantly making and unmaking itself. When particles interact, when an electron repels another electron, when a quark binds to another quark, it is not because they bump into each other like billiard balls. Instead, it is their fields that interact, overlapping and influencing one another in ways that can be described with exquisite mathematical precision. Physicists use diagrams, little sketches called Feynman diagrams, to visualize these interactions. In these diagrams, particles are lines, and their meetings are points where the lines connect. A photon, a particle of light, might spring from one electron and be absorbed by another, carrying the electromagnetic force between them. These diagrams are more than pictures. They are maps of possibility, guides to calculating what happens when fields meet and mingle. Over decades, physicists have built a grand structure, a towering achievement of human thought, called the Standard Model of Particle Physics. It is a quantum field theory, a description of almost everything we know about the subatomic world. It explains 3 of the 4 fundamental forces of nature: the electromagnetic force that holds atoms together and makes light shine, the weak force that allows particles to decay and transforms one type of particle into another, and the strong force that binds quarks together inside protons and neutrons. Gravity, the 4th force, the one that keeps your feet on the ground and holds planets in their orbits, is not part of the Standard Model. It stands apart, described by Einstein's general relativity, and weaving it together with quantum field theory remains one of the great unfinished puzzles of physics. Within the Standard Model, there are different quantum field theories for different forces, each with its own character, its own mathematics, its own beauty. One of the most successful, one of the most precisely tested theories in all of science is quantum electrodynamics, the quantum field theory of electromagnetism. It describes how light and matter interact, how photons and electrons dance together. The predictions of quantum electrodynamics are astonishingly accurate, matching experiments to more than 10 decimal places, a precision so fine that it is like measuring the distance from New York to Los Angeles and being correct to within the width of a human hair. Then there is quantum chromodynamics, the theory of the strong force, the force that holds quarks together. Quarks are the building blocks of protons and neutrons, and they are bound by particles called gluons, which themselves carry the strong force. The name chromodynamics comes from the word for color, because physicists use color as a metaphor for a property quarks possess, a kind of charge that comes in three types, whimsically called red, green, and blue. These are not real colors, of course, but the metaphor helps us understand how quarks combine, how three quarks of different colors can come together to form a colorless proton or neutron, stable and strong. And finally, there is the Higgs field, perhaps the most mysterious and the most essential field of all. The Higgs field is different from the others. It fills all of space, just as the other fields do, but it does something unique. It interacts with many particles as they move through it, and in that interaction, it gives them mass. Without the Higgs field, electrons and quarks would zip through the universe at the speed of light, massless and unable to form atoms. The Higgs field is like a cosmic ocean of molasses, not slowing particles down in the usual sense, but giving them the property of mass, the property that makes them resist acceleration, that makes them heavy. In the early universe, just after the Big Bang, the Higgs field underwent a transition, settling into a state where it fills all of space with a non-zero value, and in that moment, particles acquired their masses. The discovery of the Higgs boson, the ripple in the Higgs field, in experiments at the Large Hadron Collider in 2012, confirmed this picture and completed a chapter in our understanding of the quantum fields that shape reality. So here we are, floating in an invisible sea, surrounded by fields that ripple into particles, particles that flicker into existence and vanish, forces that are carried by other particles, all described by the elegant mathematics of quantum field theory. It is a vision of the universe that is both strange and beautiful, a reminder that beneath the solid, everyday world, there is a realm of shimmering energy, of constant change, of creation and annihilation. The quantum fields are always here, always active, the foundation of everything we see and everything we are. In the year 2012, deep beneath the border between Switzerland and France, inside a tunnel 17 miles around, physicists finally saw something they had been searching for across decades. It was a particle, a tiny ripple in a field that fills all of space, and they called it the Higgs boson. This particle is the quantum of the Higgs field, the smallest possible wave, the fundamental excitation that proves the field is real. For years, scientists had predicted its existence through mathematics and theory, but now, in the debris of protons smashed together at nearly the speed of light, they found it. The discovery was a triumph, a confirmation that our equations were not just beautiful abstractions but true maps of reality. The Higgs boson appeared for only a fraction of a second before decaying into other particles, but in that brief flash, it told us that the Higgs field is there, invisible and everywhere, giving mass to the universe. And when we say these fields are everywhere, we mean truly everywhere. The electron field does not stop at the edge of your skin or at the surface of a stone. It runs through everything. The same electron field that exists in the empty space between galaxies also exists inside stars, where temperatures reach millions of degrees and matter is crushed under immense gravity. It exists inside rocks, ancient and cold, and inside living organisms, inside every cell of every plant and animal. Fields are not contained by walls or boundaries. They are the canvas on which everything is painted. Wherever there is space, wherever there is time, the fields are present, ready to ripple into particles, ready to interact and shape the world. These fields, even in their quietest state, give rise to strange and beautiful phenomena. One of the most remarkable is called the Casimir effect, named after a Dutch physicist who predicted it in the middle of the 20th century. Imagine two flat metal plates placed very close together in a vacuum, just a tiny fraction of a millimeter apart. You might think that nothing happens, that the empty space between them is truly empty. But the quantum vacuum is never empty. It seethes with virtual particles, with fluctuations in the electromagnetic field, ripples appearing and disappearing in the blink of an eye. Outside the plates, all wavelengths of these fluctuations can exist, but between the plates, only certain wavelengths fit. It is like a guitar string that can only vibrate in certain ways. Because fewer fluctuations can exist between the plates than outside them, there is a difference in pressure, and the plates are gently pushed together by the quantum vacuum itself. This force has been measured in laboratories, a whisper from the invisible fields, a reminder that the vacuum is alive with energy. Yet this vacuum energy, this zero-point energy that permeates all of space, presents one of the deepest mysteries in physics. When physicists use quantum field theory to calculate how much energy should be packed into the vacuum, the numbers they get are enormous, vastly larger than what we observe in the universe. If the vacuum energy were as large as the theory suggests, space itself would be curved so drastically that galaxies, stars, and planets could never have formed. The universe would be torn apart or collapsed in an instant. But we see a universe that is calm and orderly, a universe where the vacuum energy, if it exists at all, is incredibly tiny. This mismatch, this vast gap between theory and observation, is called the vacuum catastrophe, and it is one of the most profound puzzles in modern science. No one knows how to solve it. Perhaps there is a deep principle we have not yet discovered, some symmetry or mechanism that cancels out the vacuum energy. Or perhaps our understanding of quantum fields and gravity is still incomplete, waiting for a new insight to bring it all into harmony. Despite these mysteries, quantum field theory has given us tools of astonishing precision. One of its great achievements is the ability to calculate radiative corrections, tiny adjustments to the behavior of particles that arise from the interactions of fields. Imagine an electron orbiting a proton in a hydrogen atom, the simplest atom in the universe. According to older quantum mechanics, the electron should occupy certain energy levels, like rungs on a ladder. But quantum field theory tells us that the electron is constantly interacting with the electromagnetic field around it, emitting and reabsorbing virtual photons, flickering in and out of different states. These interactions shift the energy levels ever so slightly, by amounts so small they seem almost negligible. Yet in the 1940s, physicists measured one of these shifts, called the Lamb shift, and found that quantum field theory predicted it with stunning accuracy. The theory accounted for every decimal place, every tiny fraction of energy. It was a moment of profound validation, proof that the quantum fields are not just mathematical fantasies but real aspects of nature. And this is the remarkable thing about quantum field theory. Even though it is filled with conceptual puzzles, even though it predicts vacuum energies that seem wildly wrong, even though its mathematics can be bewildering and incomplete, it is one of the most accurate frameworks in all of science. Some of its predictions have been confirmed to over 10 significant figures, a level of precision that is almost unimaginable. It is as if you could predict the distance from the Earth to the Moon and be correct to within the thickness of a sheet of paper. Quantum field theory works, and it works spectacularly well, even as we struggle to understand fully why it works or what it means. But the theory is not finished. There are gaps, places where our understanding falters. The most glaring is gravity. We have a beautiful theory of gravity, Einstein's general relativity, which describes how mass and energy curve spacetime, how planets orbit stars, and how light bends around black holes. But general relativity is not a quantum theory. It does not describe gravity in terms of fields and particles in the way that quantum field theory does for the other forces. Physicists have tried for nearly a century to build a quantum field theory of gravity, to describe gravitons, the hypothetical particles that would carry the gravitational force. But every attempt has run into problems. The mathematics becomes uncontrollable, infinities pile up, and predictions lose meaning. A consistent, experimentally verified quantum field theory of gravity does not yet exist. Gravity stands apart, and uniting it with quantum field theory remains one of the great dreams of physics. Even the mathematics of quantum field theory, the very foundation on which it rests, is not fully understood. The theories that describe electromagnetism, the strong force, and the weak force are called interacting quantum field theories, because the fields do not just sit quietly, they interact with themselves and with each other. In 4 dimensions of space-time, the 3 dimensions of space we move through and the 1 dimension of time we march along, the mathematical structure of these interacting theories is still not completely rigorous. There are formulas that work, techniques that give correct answers, but the deep logical foundation, the kind of foundation that mathematicians demand, is still missing. This is not just a technical detail. It is an open problem, a challenge that sits at the intersection of physics and mathematics, waiting for someone to solve it, to show that the machinery of quantum field theory rests on solid ground. Within quantum field theory, the forces of nature are described in a surprising way, through something called gauge symmetries. A gauge symmetry is a kind of redundancy in the way we describe a field. It is like having multiple maps of the same territory, maps that look different but describe the exact same landscape. In quantum field theory, these redundancies are not just mathematical curiosities, they are the essence of forces. The electromagnetic force arises from a gauge symmetry of the electromagnetic field. The requirement that the theory be unchanged under certain transformations forces the existence of the photon, the particle that carries the electromagnetic force. It is a deep and beautiful idea. Forces are not added to the theory by hand but emerge naturally from the symmetries of the fields. And some of these gauge theories are even stranger. They are called non-abelian gauge theories, named after the mathematician Niels Henrik Abel. In these theories, the gauge fields themselves can interact with one another. The gluons that carry the strong force, for example, do not just pass between quarks like messengers. They interact with each other, pulling and pushing, creating a rich and complex web of forces. This self-interaction makes the strong force behave in unusual ways. At very short distances, quarks act almost as if they are free, barely interacting. But try to pull them apart, and the force grows stronger, binding them together so tightly that quarks are never seen alone. This is the realm of quantum chromodynamics, where the fields themselves become actors in the drama, not just the stage on which it unfolds. Deep inside protons and neutrons, in a space smaller than a billionth of a meter, quarks are bound together by the strong force, held by gluons in a grip so tight that no quark has ever been seen alone. Yet if you could look closely enough, if you could probe these particles at incredibly high energies, smashing them together with tremendous force, something surprising happens. The quarks begin to act almost as if they are free, as if the strong force that binds them has weakened and let go. This strange behavior is called asymptotic freedom, and it is one of the most unexpected features of non-abelian gauge theories, the mathematical structures that describe the strong force. At very short distances, at very high energies, the interactions between quarks become weaker and weaker. It is the opposite of what happens in everyday experience, where forces usually grow stronger as objects get closer. But in the world of quantum chromodynamics, closeness brings freedom, and separation brings confinement. This discovery, made in the early 1970s, helped physicists understand how quarks behave inside hadrons, the family of particles that includes protons and neutrons, and it earned its discoverers a Nobel Prize. Yet quantum field theory is not without its challenges, not without its infinities. When physicists first tried to calculate the properties of particles using the equations of quantum fields, they found that many of their answers came out infinite, impossibly large, without meaning. For a time, this seemed like a fatal flaw, a sign that the theory was broken. But then a remarkable insight emerged, a process called renormalization. Renormalization is a way of dealing with infinities by absorbing them into the parameters of the theory, into quantities like mass and charge that we measure in experiments. We take the infinite contributions and fold them into redefinitions of these parameters, and what remains are finite, physically meaningful predictions. It is a delicate procedure, almost like a magic trick, but it works. The predictions that come out match experiments with astonishing precision. Renormalization does not explain why the infinities appear, but it tames them, turning a seemingly broken theory into one of the most powerful tools in physics. And renormalization reveals something deeper, something beautiful. The parameters of quantum field theory, the numbers that describe the strength of forces, are not truly constant. They change depending on the energy scale at which you measure them. This idea is captured by the renormalization group, a mathematical framework that describes how coupling constants, the numbers that tell you how strongly particles interact, run with energy. At low energies, the electromagnetic force has one strength. At high energies, it has another. The force evolves, shifting and changing as you zoom in or zoom out, like a landscape that looks different from different altitudes. This running of coupling constants is not a flaw but a feature, a window into the way quantum fields behave across the vast range of scales in the universe, from the enormous distances between galaxies to the tiny scales inside atomic nuclei. Not all quantum field theories can be renormalized in this way. Some theories, when you try to remove their infinities, resist. They are called non-renormalizable theories, and they cannot make predictions at arbitrarily high energies. But this does not mean they are useless. Instead, they are treated as effective theories, descriptions that work beautifully up to a certain energy scale but break down beyond it. General relativity itself, when treated as a quantum field theory, is non-renormalizable. It works perfectly to describe gravity at the energies we can access, but it suggests that at higher energies, perhaps near the Planck scale, where quantum effects and gravity become equally important, a deeper, more complete theory is needed. Quantum fields also give rise to a phenomenon called spontaneous symmetry breaking, a process that is central to our understanding of mass and forces. Imagine a perfectly symmetric sphere, smooth and round, balanced at the top of a hill. The equations that describe this system are symmetric, treating all directions equally. But the sphere cannot stay balanced forever. It must roll down the hill, and when it does, it chooses a direction, breaking the symmetry. The equations are still symmetric, but the solution, the state the system settles into, is not. This is spontaneous symmetry breaking, and it happens in quantum fields. The equations of motion for a field might be symmetric, but the vacuum state, the lowest energy configuration, might not be. The field settles into a particular value, choosing one possibility among many, and in that choice, symmetry is broken. This kind of symmetry breaking requires something special. It requires an infinite number of degrees of freedom, an infinite number of possible ways for the field to vibrate and oscillate. In a finite system, like a small number of particles, symmetry breaking can be undone by quantum fluctuations. But in a quantum field, which extends throughout all of space, the symmetry can be broken permanently, locked into the structure of the vacuum itself. This is why spontaneous symmetry breaking is a phenomenon of fields, not of individual particles. When a continuous symmetry is broken spontaneously, something remarkable emerges: massless particles called Nambu-Goldstone bosons. These are ripples in the field, excitations that cost no energy to create because they correspond to sliding along the direction in which the symmetry was broken. They appear in the spectrum of the theory like ghosts, massless and ethereal, a signature that symmetry has been lost. But in gauge theories, something even stranger can happen. There is a version of spontaneous symmetry breaking called the Higgs mechanism, and it allows gauge bosons, the particles that carry forces, to acquire mass while preserving the deeper symmetry of the theory. Normally, gauge bosons, like the photon, are massless because of the symmetry of the gauge theory. But when the Higgs field settles into a non-zero value in the vacuum, breaking the symmetry, the gauge bosons can eat the would-be Nambu-Goldstone bosons, absorbing them and gaining mass in the process. The photon remains massless because electromagnetism symmetry is not broken, but the W and Z bosons, which carry the weak force, gain mass through this mechanism. It is an elegant solution, a way to have massive force carriers without destroying the mathematical consistency of the theory. All of these ideas, asymptotic freedom, renormalization, spontaneous symmetry breaking, rest on the foundation of Yang-Mills theories, a generalization of Maxwell's electromagnetism to non-abelian gauge groups. Maxwell's equations described the electromagnetic field, a single field with a simple symmetry. Yang-Mills theories extend this to more complex symmetries, where multiple fields are intertwined and can rotate into one another. These theories form the backbone of the Standard Model's gauge sector, describing the strong and weak forces with the same mathematical elegance that Maxwell used for electromagnetism. Yet despite their success, Yang-Mills theories are not fully understood. Establishing a completely rigorous interacting Yang-Mills quantum field theory in 4 dimensions, proving that it exists mathematically and has a mass gap, a minimum energy above the vacuum, is one of the Clay Millennium Prize problems, one of the great unsolved puzzles in mathematics. Physicists use Yang-Mills theories every day, calculating scattering amplitudes and predicting particle behavior, but the deep mathematical foundation is still incomplete. It is a humbling reminder that even our most powerful theories rest on ground that is not yet fully solid, that there are mysteries still waiting to be unraveled. And then there are anomalies, places where the quantum world refuses to respect the symmetries of the classical equations. In classical physics, if your equations have a symmetry, a transformation that leaves them unchanged, you expect that symmetry to hold in all solutions, in all physical processes. But in quantum field theory, symmetries can be broken by quantum effects themselves. This is called a quantum anomaly, and it occurs when the path integral, the mathematical tool used to calculate quantum probabilities, fails to preserve a symmetry that the classical equations possess. It is a subtle and surprising phenomenon, a reminder that quantization is not always a straightforward process. One of the most famous anomalies is the Adler-Bell-Jackie anomaly, named after the physicists who discovered it. For years, there was a puzzle in particle physics. The neutral pion, a particle made of quarks, decays into 2 photons, 2 particles of light. But according to classical symmetry arguments, this decay should be forbidden or at least heavily suppressed. The anomaly resolved the puzzle. The symmetry that seemed to forbid the decay is broken by quantum effects, and the pion decays just as experiments showed it should. The anomaly turned a mystery into a prediction, a triumph of quantum field theory. But not all anomalies are benign. Gauge anomalies, anomalies in the symmetries that define the forces themselves, are dangerous. If a gauge anomaly is present in a theory, it leads to inconsistencies, to probabilities that do not add up to 1, to unphysical states that should not exist. For a quantum field theory to be consistent, its gauge anomalies must vanish, must cancel out exactly. This is a stringent requirement, a test that every candidate theory must pass. The Standard Model passes this test beautifully. The anomalies that would arise from its quarks and leptons cancel each other precisely, a delicate balance that hints at deep structure. Anomalies can be computed using Feynman diagrams, particularly a diagram shaped like a triangle, involving a loop with fermions coupling to 3 gauge bosons. This triangle diagram captures the essence of the anomaly, showing how quantum corrections can violate classical symmetries. There are also global anomalies, which do not make the theory inconsistent but still affect physical processes. They can lead to effects like instant and induced baryon number violation, rare quantum tunneling events that change the number of baryons, the particles like protons and neutrons. These processes are incredibly suppressed in our universe, but the anomalies tell us they are possible in principle, woven into the fabric of quantum field theory. A profound principle called T-Hooft anomaly matching states that anomalies in a high-energy theory must match those in its low-energy effective theory. Symmetries and their anomalies are robust, surviving the transition from one description to another, providing a powerful tool for understanding the relationship between different theories. In odd-dimensional spacetimes, chiral anomalies can lead to anomaly inflow, where anomalies in the bulk are cancelled by contributions from the boundary. This idea appears in condensed matter physics in the quantum Hall effect, where edge states carry currents that balance anomalies in the interior. Anomalies come in different types. Consistent anomalies satisfy certain mathematical conditions, the Wess-Zumino consistency conditions, ensuring that they behave in a controlled way. Covariant anomalies transform predictably under gauge transformations, respecting the structure of the theory even as they break symmetries. Gravitational anomalies arise when chiral fermions couple to gravity. For a consistent theory of quantum gravity, these anomalies must cancel, just as gauge anomalies must. This requirement places constraints on any attempt to unify quantum field theory with general relativity, adding another layer to the puzzle of quantum gravity. Finally, anomalies are topological invariants, quantities that do not change when you smoothly deform the theory or adjust the way you regulate infinities. They are deep, fundamental features, carved into the structure of quantum field theory, insensitive to details, revealing the underlying shape of the quantum world. In the quiet depths of quantum field theory, where mathematics meets the fundamental laws of nature, there are moments when symmetry, that guiding principle of physics, breaks down in unexpected ways. These moments are called quantum anomalies, and they arise when a symmetry that exists perfectly in the classical equations fails to survive the transition to the quantum world. Imagine writing down equations that are beautifully symmetric, balanced, and elegant, only to find that when you calculate quantum corrections, when you account for the probabilistic nature of particles and fields, the symmetry vanishes like morning mist. This happens because of subtle effects in the path integral, the mathematical tool that sums over all possible histories of a quantum system. The measure, the way we count and weight these histories, can itself break the symmetry, introducing anomalies that were invisible at the classical level. One of the most celebrated examples of such an anomaly is the Adler-Bell-Jackie anomaly, named after three physicists who independently discovered it in the late 1960s. For years, particle physicists had observed a curious phenomenon. The neutral pion, a fleeting particle composed of a quark and an antiquark, decays into two photons, two particles of pure light. According to classical reasoning, according to symmetry arguments that seemed ironclad, this decay should have been forbidden, or at least so rare as to be nearly impossible. The symmetry in question was chiral symmetry, a kind of left-right balance in the behavior of quarks. But experiments showed the decay happening readily, and no one could explain why. The anomaly resolved the puzzle. The chiral symmetry, so perfect in the classical theory, is broken by quantum effects. The path integral does not respect it. The symmetry is lost, and the pion decays into photons just as nature shows us. It was a moment of revelation, turning a contradiction into a prediction, transforming confusion into understanding. But not all anomalies are harmless. Some are dangerous, threatening the very consistency of the theory. These are called gauge anomalies, anomalies in the symmetries that define the forces of nature. Gauge symmetries are not optional decorations, they are the foundation on which quantum field theories of forces are built. If a gauge anomaly is present, if the quantum theory fails to preserve these symmetries, the consequences are severe. The theory becomes non-unitary, meaning that probabilities no longer add up to 1. Unphysical states, states that should not exist, can appear in the calculations, ghosts that haunt the equations and make predictions meaningless. For a quantum field theory to be consistent, for it to describe a possible universe, its gauge anomalies must vanish. They must cancel out exactly, leaving no trace. This is a stringent requirement, a filter that only the most carefully constructed theories can pass. Physicists have developed tools to detect and calculate these anomalies, and one of the simplest and most elegant is the triangle diagram in Feynman perturbation theory. Picture a loop, a closed path in spacetime where a fermion, a matter particle like an electron or a quark, travels in a circle, interacting with three gauge bosons, the particles that carry forces. This diagram, shaped like a triangle, captures the essence of many anomalies. By calculating the quantum corrections represented by this loop, physicists can determine whether a symmetry is preserved or broken, whether the theory is safe or flawed. The triangle diagram is a window into the quantum world, revealing the hidden structure of fields and forces. There are also global anomalies, anomalies in symmetries that are not tied to the forces themselves but to other properties of the theory. Unlike gauge anomalies, global anomalies do not destroy the consistency of the theory. They do not make probabilities fail or introduce unphysical states. But they still have consequences. They affect rare processes, subtle quantum events that would otherwise be forbidden. One such process is instant and induced baryon number violation, a phenomenon where the number of baryons, particles like protons and neutrons, can change through quantum tunneling. In our everyday world, baryon number seems to be conserved. Protons do not decay spontaneously, at least not on timescales we can measure. But the global anomaly tells us that at high energies, in the extreme conditions of the early universe, baryon number can be violated. Instantons, special solutions to the equations of the gauge fields, can mediate this violation, allowing processes that transform matter in fundamental ways. These effects are incredibly rare, suppressed by factors so small that they are negligible in the present-day universe, but they are permitted by the theory, woven into the quantum fabric. A deep principle discovered by the physicist Gerard T. Hooft states that anomalies must match between a high-energy theory and its low-energy effective description. This is called T. Hooft anomaly matching, and it is a powerful tool for understanding how different theories relate to each other. Imagine you have a theory that describes physics at very high energies, where particles and fields are resolved in great detail. Now imagine you zoom out, looking at lower energies where some of the details blur and the theory simplifies into an effective description. The T. Hooft anomaly matching condition says that the anomalies in both descriptions must be the same. Symmetries and their violations are robust features, surviving the transition from one scale to another, providing a fingerprint that links the microscopic and macroscopic worlds. In theories with odd numbers of spacetime dimensions, chiral anomalies can lead to a phenomenon called anomaly inflow, where anomalies in the bulk of space are cancelled by contributions from the boundary. This idea, abstract and mathematical, finds concrete realization in condensed matter physics in systems like the quantum Hall effect. In the quantum Hall effect, electrons confined to a two-dimensional plane in a strong magnetic field exhibit strange and beautiful behavior. The bulk of the material is insulating, but the edges carry currents that flow without resistance, protected by topology. The anomaly in the bulk, the violation of charge conservation due to the magnetic field and quantum effects, is precisely balanced by the current flowing along the edge. The anomaly flows from the interior to the boundary, where it manifests as physical, measurable phenomena. It is a striking example of how abstract quantum field theory concepts connect to real experiments, to systems you can build and measure in a laboratory. Anomalies come in different mathematical flavors, different ways of formalizing how symmetries are broken. Consistent anomalies satisfy a set of conditions called the Wess-Zumino consistency conditions, equations that ensure the anomaly behaves in a controlled, predictable way under repeated symmetry transformations. Covariant anomalies, on the other hand, transform in a specific manner under gauge transformations, respecting the structure of the theory even as they violate the symmetry. These distinctions, technical and subtle, matter because they determine how anomalies affect calculations and physical predictions. When chiral fermions, particles whose left-handed and right-hand versions behave differently, are coupled to gravity, they can give rise to gravitational anomalies. Just as gauge anomalies threaten the consistency of theories of forces, gravitational anomalies threaten the consistency of theories that try to combine quantum mechanics with general relativity. For a theory of quantum gravity to be viable, its gravitational anomalies must cancel. This requirement places stringent constraints on any candidate theory, adding another challenge to the already formidable task of unifying quantum field theory with Einstein's curved spacetime. Finally, anomalies are topological invariants, quantities that depend only on the overall shape and structure of the theory, not on the details of how you calculate or regulate infinities. You can change the action, the fundamental equation that describes the fields. You can choose different ways to handle the infinities that arise in quantum calculations. But the anomalies remain the same. They are carved into the topology of the field configuration space, into the deep geometry of the quantum world. They are insensitive to smooth deformations, robust against changes, fundamental features that reveal the underlying order of nature. Anomalies, once seen as obstacles, are now understood as essential clues, guiding us toward deeper truths about quantum fields, symmetries, and the forces that shape the universe. They tell us which theories are possible and which are not. They reveal hidden connections between different energy scales, between bulk and boundary, between the microscopic laws and the phenomena we observe. They are reminders that the quantum world is richer and stranger than our classical intuition suggests, that symmetry and its breaking are not simple concepts but layered, nuanced, and endlessly fascinating. In the stillness of the vacuum, in the silent dance of virtual particles, in the equations that describe forces and matter, anomalies stand as markers of the extraordinary, as whispers from the deepest levels of reality. There is another way to think about quantum field theory, a way that is mathematically profound and conceptually beautiful. It is called the path integral formulation, and it was developed by Richard Feynman in the middle of the 20th century. In this approach, you do not think of a particle following a single trajectory through space and time. Instead, you imagine that it explores every possible path, every conceivable route from its starting point to its destination. Each path, each configuration of the field, is assigned a weight, a number determined by the action, a quantity that measures the difference between kinetic and potential energy along that path. The weight is given by an exponential function, e raised to the power of I times the action divided by Planck's constant. The transition amplitude, the probability for the field to evolve from one state to another, is then an integral, a sum over all possible field configurations, each contributing its weighted share. It is a vision of reality where every possibility matters, where the quantum world is built from the superposition of all conceivable histories. Within this framework, there are special solutions called instantons, exotic configurations that are not visible in ordinary perturbation theory. Instantons live in Euclidean space, a mathematical cousin of space-time where time is imaginary, rotated into a form that makes certain calculations easier. They are saddle points in the path integral, configurations where the action is stationary, neither a minimum nor a maximum but a delicate balance. Instantons mediate tunneling, quantum processes where a system leaps from one vacuum state to another, crossing barriers that would be insurmountable in classical physics. They are non-perturbative, meaning they cannot be found by making small corrections to simple solutions. They are entirely new, arising from the global structure of the theory, from the topology of the fields. In quantum chromodynamics, the theory of the strong force, instantons give rise to something called the theta vacuum. The vacuum is not unique. There are infinitely many possible vacuum states, each labeled by a topological winding number, an integer that counts how the gluon fields twist and wrap through space. These states cannot be smoothly deformed into one another, they are separated by barriers. The true vacuum of QCD is a superposition of all these topologically distinct states, and the way they mix is controlled by a parameter called theta. This parameter, a single number, determines the weight given to each winding sector, and it has profound consequences. One of these consequences is a puzzle known as strong CP violation. The letters CP stand for charge conjugation and parity, symmetries that reverse the charge and mirror the spatial coordinates of particles. In principle, The theta parameter allows QCD to violate CP symmetry, leading to observable effects like an electric dipole moment for the neutron, a tiny imbalance in its charge distribution. But experiments show that if such an effect exists, it must be extraordinarily small, far smaller than the theta parameter would naturally suggest. This is the strong CP problem. Why is theta so close to zero? One proposed solution is the existence of a new particle called the axion, introduced through the Peccei-Quinn mechanism. The axion is a light, weakly interacting particle whose field dynamically adjusts to cancel the theta parameter, driving it to zero and preserving CP symmetry. Instantons play a key role in this mechanism, generating the potential that allows the axion to do its work. If axions exist, they could also be a component of dark matter, the invisible substance that holds galaxies together. Quantum field theory also allows for magnetic monopoles, hypothetical particles that carry isolated magnetic charge, the magnetic equivalent of an electron's electric charge. In classical electromagnetism, magnetic monopoles do not exist. Magnetic field lines always form closed loops. There are no isolated north or south poles. But in quantum theory, the physicist Paul Dirac showed that monopoles could exist if the vector potential, the mathematical object that describes the electromagnetic field, is allowed to have a singularity, a line called the Dirac string stretching away from the monopole. The electric and magnetic charges of particles must then satisfy a quantization condition, a precise relationship that ensures the string is unobservable. This condition links electricity and magnetism in a deep way, suggesting that monopoles, if they exist, would reveal a hidden symmetry in nature. In non-abelian gauge theories with Higgs fields, monopoles can arise as soliton solutions, stable configurations of fields that carry magnetic charge. These are called T. Hooft-Polyakov monopoles, named after Gerard T. Hooft and Alexander Polyakov, who discovered them independently. Unlike Dirac monopoles, which require a string singularity, T. Hooft-Polyakov monopoles are smooth, regular solutions, stabilized by topology. The fields wrap around the monopole in a way that cannot be unwound, locking the magnetic charge in place. These monopoles are predicted to be extremely massive, far beyond the reach of current experiments, but they play an important role in theories of the early universe and in models that extend the Standard Model. To probe the structure of gauge theories, especially the question of confinement, physicists use a mathematical tool called a Wilson loop. A Wilson loop is a closed path in spacetime, and you calculate it by following the gauge field around that path, accumulating a phase. In theories where quarks are confined, where they cannot be separated, the Wilson loop obeys an area law. The phase depends on the area enclosed by the loop, not just its perimeter. This area law is a signature of confinement, indicating that pulling quarks apart requires energy proportional to the distance between them, energy that eventually creates new quark-antiquark pairs. In quantum chromodynamics, at low energies, Wilson loops obey this area law, confirming that quarks are permanently bound. In contrast, in theories without confinement, the Wilson loop obeys a perimeter law, growing only with the length of the path. The way quantum field theories change with energy scale is governed by equations that capture the flow of parameters, the evolution of coupling constants and masses as you zoom in or out. One such equation is the Callant-Symanzik equation, which relates how correlation functions, the probabilities for fields to take certain values at different points, depend on the energy scale. This dependence is controlled by the beta function, which tells you how the coupling constant changes, and by anomalous dimensions, which describe how fields themselves scale. The Kalan-Symanzik equation is a window into the renormalization group, the mathematical framework that organizes how theories behave at different scales. At the heart of this framework is the beta function, a small but mighty object. It is usually written as beta of g, where g is the coupling constant, and it describes how g changes with the energy scale, measured by the logarithm of the scale mu. The equation is simple. The derivative of g with respect to the logarithm of mu is equal to the beta function. But the consequences are vast. If the beta function is negative, the coupling decreases at high energies, as in asymptotic freedom. If it is positive, the coupling grows. The beta function encodes the dynamics of the theory, the way forces strengthen or weaken as you probe shorter or longer distances. Sometimes, the beta function vanishes. The coupling constant stops running, frozen at a particular value. These are called fixed points of the renormalization group flow, and they correspond to conformal field theories, theories that are symmetric under changes of scale. Conformal field theories describe critical phenomena, the behavior of systems at phase transitions, like water at its boiling point or a magnet at its Curie temperature. At these critical points, the system looks the same at all length scales, exhibiting self-similarity, patterns that repeat at every magnification. The renormalization group flows toward these fixed points, and studying them reveals universal properties, features that do not depend on the microscopic details but only on the symmetries and dimensionality of the system. The path integral, instantons, monopoles, Wilson loops, the Kalan-Symanzik equation, the beta function, fixed points. These are the tools and concepts that allow physicists to explore the full richness of quantum field theory, to understand not just individual particles but the collective behavior of fields, the way they interact, the way they confine, the way they flow across scales. They are reminders that quantum field theory is not a static edifice but a living structure, evolving and revealing new facets as we probe deeper, as we ask new questions, as we push the boundaries of what we can calculate and understand. In the silence of the vacuum, in the twisting of fields through space, in the flow of coupling constants with energy, the universe writes its deepest secrets, waiting for us to read them. There exist quantum field theories that possess an extraordinary symmetry, a symmetry so powerful that it constrains almost every aspect of the theory. These are called conformal field theories, and they are invariant under conformal transformations, changes in spacetime that preserve angles but allow lengths to stretch and shrink arbitrarily. Imagine looking at a shape through a lens that distorts distances but keeps corners and angles intact. Conformal field theories look the same under such transformations. They have no preferred scale, no characteristic length. They are scale invariant, appearing identical whether you zoom in or zoom out, and this symmetry gives them a special elegance, a mathematical purity that makes them both beautiful and tractable. In conformal field theories, there is a powerful tool called the operator product expansion, often abbreviated as OPE. When two operators, mathematical objects that represent physical quantities like fields or currents, are brought close together in spacetime, their product can be expressed as a sum of other operators. Each term in the sum comes with a coefficient and a power that depends on the scaling dimension, a number that tells you how the operator transforms under changes of scale. The operator product expansion organizes the behavior of the theory at short distances, revealing how complex interactions emerge from simpler building blocks. It is a kind of algebra, a set of rules that govern how operators multiply and combine, and it is central to understanding the structure of conformal field theories. In two-dimensional conformal field theories, theories that live on a plane or on surfaces like a sphere or a torus, There is a special number called the central charge, denoted by the letter C. The central charge measures something subtle, the trace anomaly, a quantum effect where the stress-energy tensor, the object that describes energy and momentum, fails to be traceless even though classical symmetry suggests it should be. The central charge also counts the effective degrees of freedom in the theory, the number of independent ways the fields can fluctuate. It is a fingerprint of the theory, a number that distinguishes one conformal field theory from another. A theory with central charge C equals 1/2 describes a single free fermion. A theory with C equals 1 describes a free boson. Higher central charges correspond to more complex, richer theories. The symmetry of two-dimensional conformal field theories is captured by an infinite-dimensional algebra called the Virasoro algebra. This algebra extends the conformal group, the group of conformal transformations, with a central extension, an extra term that encodes the central charge. The Virasoro algebra governs the operator algebra of the stress-energy tensor, dictating how energy and momentum flow and transform. It is a powerful structure, and its representation theory, the study of how it acts on different states, organizes the entire spectrum of the conformal field theory, classifying all possible states and their symmetries. When a conformal field theory is placed on a torus, a donut-shaped surface, its partition function, the sum over all states weighted by their energy, must satisfy a property called modular invariance. The torus can be described in different ways, with different choices of fundamental cycles, and modular invariance says that the partition function must be the same regardless of which description you choose. This imposes stringent constraints on the spectrum of the theory and on the fusion rules, the coefficients that appear in the operator product expansion. Modular invariance is a consistency condition, a test that rational conformal field theories, a special class with finite numbers of primary operators, must pass. It links geometry and quantum field theory in a deep way, showing how the shape of space constrains the behavior of fields. In recent years, physicists have developed powerful techniques called conformal bootstrap methods to explore conformal field theories. The bootstrap does not rely on a Lagrangian, the usual starting point for quantum field theory. Instead, it uses consistency conditions, requirements that the theory must satisfy to be coherent. Chief among these is crossing symmetry, the statement that a scattering process can be calculated in different orders and must give the same answer. Combined with unitarity, the requirement that probabilities are positive and add up to 1, crossing symmetry constrains the data of the conformal field theory. The scaling dimensions, the OPE coefficients, the spectrum of operators. By solving these constraints numerically, physicists can explore the space of possible conformal field theories, discovering new theories and understanding old ones in unprecedented detail. The bootstrap is a window into the landscape of quantum field theory, revealing islands of consistency in the vast sea of mathematical possibilities. Quantum field theory is not confined to the realm of elementary particles. Its methods and ideas reach into condensed matter physics, the study of materials like metals, insulators, and superconductors. One area where quantum field theory plays a crucial role is in topological quantum field theories, which describe systems where global topological properties, rather than local order parameters, characterize the phase of matter. The quantum Hall effect is a prime example. When electrons are confined to a two-dimensional plane in a strong magnetic field at very low temperatures, the material exhibits plateaus in its electrical conductance, quantized values that depend only on fundamental constants. This behavior arises from topological invariance, numbers that characterize the way the electron wave functions twist across the sample. Topological quantum field theories capture this physics, describing states that are robust against local perturbations, protected by topology. Many phenomena in condensed matter are effectively described using the language of quantum field theory. Quasiparticles, collective excitations that behave like particles even though they are not fundamental, emerge from the interactions of countless electrons and atoms. They can have fractional charge, unusual statistics, and other exotic properties. Quantum field theory provides the tools to describe and predict their behavior, treating the solid as a medium in which effective fields propagate and interact. One of the simplest and most important quasiparticles is the phonon, a quantized vibration of a crystal lattice. When atoms in a solid oscillate, their collective motion can be decomposed into modes, each with a definite frequency and wavelength. These modes are quantized, and each quantum is a phonon, a particle of sound. Phonons carry energy and momentum. They scatter off electrons and other phonons. They mediate interactions and contribute to thermal and electrical conductivity. Describing phonons as excitations of an effective quantum field allows physicists to apply the same techniques used for photons and other particles, calculating scattering amplitudes and transport properties with precision. High-temperature superconductors, materials that conduct electricity without resistance at temperatures far higher than conventional superconductors, remain one of the great puzzles of condensed matter physics. Their behavior cannot be explained by simple theories. The electrons in these materials are strongly coupled, interacting intensely with each other and with the lattice. Quantum field theory methods are essential for modeling these systems, for describing the emergent collective excitations, the pairing mechanisms, the fluctuations that lead to superconductivity. Researchers use techniques borrowed from particle physics, renormalization group methods, gauge theories, to explore the phase diagrams and predict properties. It is a frontier where quantum field theory meets experiment, where abstract mathematics illuminates the behavior of real materials. Conformal field theories, topological quantum field theories, effective theories of quasiparticles and phonons. These are testaments to the universality of quantum field theory, its power to describe not just the fundamental particles and forces, but also the rich, complex phenomena that emerge when many particles interact. The methods are the same, whether you are calculating the scattering of quarks inside a proton or the transport of heat through a crystal. The language is the same, whether you are describing the vacuum of the early universe or the ground state of a superconductor. Quantum field theory is a bridge between scales, between disciplines, between the very small and the moderately small, between the abstract and the applied. It is a testament to the unity of physics, to the idea that the same deep principles govern the behavior of matter and energy across the entire cosmos, from the heart of a neutron star to the circuits in a quantum computer, from the first moments after the Big Bang to the quiet hum of a refrigerator on a summer night. To make quantum field theory fully precise, to turn it into something that can be calculated with computers and tested against experiments, physicists often place the fields on a discrete space-time lattice, a grid of points separated by tiny intervals. This is called lattice regularization, and it transforms the continuous fabric of space-time into a checkerboard, a finite collection of sites where fields can live and interact. On the lattice, there are no infinities from arbitrarily short distances, no ultraviolet divergences, because there is a shortest distance, the spacing between lattice points. Lattice regularization provides a non-perturbative framework, a way to study quantum field theory without relying on perturbation theory, without assuming that interactions are weak. It is used extensively in lattice QCD, the numerical study of quantum chromodynamics, where powerful computers simulate the behavior of quarks and gluons on enormous lattices, calculating the masses of protons and neutrons, the properties of mesons, and the dynamics of the quark-gluon plasma that filled the universe microseconds after the Big Bang. Lattice regularization is just one of many schemes that physicists have invented to tame the infinities that plague quantum field theory. Another is dimensional regularization, where you calculate quantities not in the usual 4 dimensions of spacetime but in a slightly different number of dimensions, perhaps 4 minus epsilon, where epsilon is a small number. The infinities become poles, singularities in epsilon, and you can isolate and remove them systematically. There is also Pauli-Villars regularization, which introduces fictitious heavy particles that cancel divergences, and many others. Each regularization scheme has its advantages and disadvantages, its own technical quirks. The remarkable thing is that, after renormalization, after you absorb the infinities into redefinitions of parameters, all these schemes give the same physical predictions. The choice of regularization is like choosing a coordinate system. It affects the intermediate steps but not the final answer. One of the deepest insights into renormalization came from Kenneth Wilson, who developed the idea of Wilsonian effective field theories. In this approach, you divide the field modes into low momentum modes and high momentum modes, separating long wavelength fluctuations from short wavelength ones. You then integrate out the high momentum modes, summing over all their possible configurations and absorbing their effects into an effective action that describes only the low energy physics. The cutoff, a momentum scale denoted by the Greek letter lambda, marks the boundary between the two regimes. As you lower the cutoff, as you integrate out more and more modes, the effective action changes, flowing through a landscape of theories. This flow is the renormalization group flow, and it is governed by equations that tell you how coupling constants and masses evolve as you change the scale. One such equation, particularly elegant and powerful, is Polchinski's flow equation, named after the physicist Joseph Polchinski. It governs the renormalization group flow of the Wilsonian effective action as the cutoff scale changes continuously. The equation is a differential equation, describing the infinitesimal change in the action as you lower the cutoff by a tiny amount. It captures the interplay between integrating out modes and the running of couplings, and it has been used to prove results about the structure of quantum field theory, to explore the space of possible theories, and to understand the behavior of theories near fixed points. Another important object in quantum field theory is the quantum effective action, sometimes called the one-particle irreducible effective action. It is a generating functional for one-particle irreducible correlation functions, the building blocks from which all scattering processes can be constructed. The quantum effective action incorporates all quantum corrections beyond the classical action, summing up the effects of loops, virtual particles, and fluctuations. It is a tool for systematic calculations, allowing physicists to go beyond leading-order approximations and compute higher-order corrections with precision. To connect the abstract machinery of correlation functions to actual scattering experiments, physicists use a formula called the LSZ reduction formula, named after Learman, Szymanczyk, and Zimmermann. The formula relates S-matrix elements, the probabilities for particles to scatter and transform, to the Fourier transforms of time-ordered correlation functions. You take a correlation function, which describes how fields are correlated at different spacetime points, and you apply wave packet smearing and Klein-Gordon operators, mathematical procedures that extract the physical on-shell scattering amplitude from the correlation function. The LSZ formula is a bridge between the formal mathematics of quantum field theory and the numbers that experimentalists measure in detectors. The S matrix itself, the matrix that encodes all possible scattering processes, has deep properties. It is unitary, meaning that the sum of probabilities for all possible outcomes of a scattering event is 1. Probability is conserved. Nothing is lost. The S matrix is also Lorentz invariant, the same in all inertial reference frames, whether you are at rest or moving at a constant velocity. This invariance ensures that the laws of physics do not depend on your state of motion, that scattering amplitudes transform correctly under boosts and rotations. From the unitarity of the S matrix comes a beautiful result called the optical theorem. It relates the total cross-section for a scattering process, the measure of how likely particles are to interact, to the imaginary part of the forward scattering amplitude, the amplitude for particles to scatter without changing direction. The theorem is a consequence of probability conservation, a statement that the sum of probabilities for all possible outcomes, including the possibility that particles pass through each other without scattering, must equal 1. The optical theorem has been verified in countless experiments, from high-energy collisions at particle accelerators to the scattering of light by atoms. Despite the success of quantum field theory, there is a desire among some physicists and mathematicians to place it on a fully rigorous foundation, to prove that it exists and is well-defined according to the strict standards of mathematical logic. This effort is called axiomatic quantum field theory, and it was pioneered by Arthur Whiteman and others in the mid-20th century. The Whiteman axioms impose a set of postulates on the vacuum expectation values of fields, the average values of field operators in the vacuum state. The axioms require relativistic invariance, ensuring the theory respects special relativity. They require positivity, ensuring that probabilities and energies are positive. They require local commutativity or microcausality, ensuring that measurements at space-like separated points do not interfere with each other, respecting the speed of light limit on information transfer. These axioms capture the essential properties that any sensible quantum field theory should possess. But there is a profound difficulty, a theorem proved by Rudolf Hogg that casts a shadow over the axiomatic approach. Hogg's theorem states that no non-trivial interacting quantum field theory can satisfy the Whiteman axioms when the interacting fields are related to free fields by a unitary transformation. In other words, the standard procedure of starting with a free theory and turning on interactions smoothly does not work in the infinite volume limit. The interacting theory and the free theory live in inequivalent Hilbert spaces, mathematical spaces that cannot be connected by a simple transformation. Hogg's theorem reveals a deep tension in the foundations of quantum field theory, a gap between the formal manipulations that physicists use successfully every day and the rigorous mathematical structure that underlies the theory. It is a reminder that quantum field theory, for all its predictive power, still harbors mysteries, still resists complete understanding. Lattice regularization, Wilsonian effective field theory, Polchinski's flow equation, the quantum effective action, the LSZ formula, the S matrix, the optical theorem, the Whiteman axioms, Hogg's theorem. These are the tools and ideas that physicists and mathematicians use to probe the deepest levels of quantum field theory, to calculate, to prove, to understand. They are reminders that the theory is both a practical tool and a conceptual puzzle, a framework that works astonishingly well and yet raises questions that remain unanswered. In the silence of the vacuum, in the flow of couplings with scale, in the scattering of particles through space-time, the universe continues to teach us, to challenge us, to reveal its beauty and its mystery one theorem, one calculation, one insight at a time. When particles scatter, when they come together from distant regions of space, collide, and then fly apart, quantum field theory must describe not just the collision itself but also the asymptotic states, the states of particles infinitely far in the past before they interact and infinitely far in the future after the interaction is complete. In the standard approach, these asymptotic states are often constructed by assuming that interactions gradually turn off at large distances and times, letting the fields become free. But this assumption is problematic, especially in light of Hogg's theorem. An alternative was developed by Rudolf Hogg and David Ruel, called Hogg-Ruel scattering theory. This approach constructs asymptotic particle states directly from smeared field operators in the interacting theory, without assuming a free field limit. It uses wave packets, localized bundles of energy and momentum, and shows that under certain conditions, these wave packets evolve into well-defined particle states in the distant past and future. The Hogg-Ruel theory provides a rigorous foundation for scattering in quantum field theory, sidestepping some of the difficulties that plague less careful approaches. The Whiteman axioms impose stringent requirements on the structure of correlation functions, and one of these requirements is analyticity. The vacuum two-point function, the simplest correlation function, must be analytic in a primitive domain of complexified momenta. This means that when you extend the momenta from real numbers to complex numbers, the function has no singularities in certain regions of the complex plane. Analyticity is a powerful constraint. It enables the derivation of dispersion relations, equations that relate the real and imaginary parts of scattering amplitudes, expressing one in terms of the other through integrals. Dispersion relations have been used to test the consistency of quantum field theory, to extract information about particle interactions from experimental data, and to connect low-energy and high-energy physics. A particularly important result is the Corlin-Learman spectral representation, which expresses the two-point function as an integral over a positive spectral density, denoted by the Greek letter ρ, weighted by free propagators. The spectral density is a function of the invariant mass squared, mu squared, and it encodes all the information about the particles and resonances that can propagate between the two field insertions. The representation starts at a threshold, the minimum value of mu squared, which is the mass squared of the lightest state that can be created. Beyond this threshold, the spectral density captures the contributions of all heavier states, including multiparticle continua and bound states. The Corlin-Learman representation is a sum rule, a way of decomposing the complicated interacting propagator into a weighted sum of free propagators for all possible intermediate states. It is a bridge between the abstract field operators and the physical spectrum of the theory. The spectral density itself is a rich object. It tells you the masses of particles and the couplings that govern their creation and annihilation. It is always positive, a reflection of unitarity, the requirement that probabilities are non-negative. The shape of the spectral density, the way it rises and falls with mu squared, reveals the dynamics of the theory, the presence of resonances, the strength of interactions. Measuring the spectral density is one of the goals of high-energy experiments, where particles are created and their properties studied. One of the fundamental requirements of quantum field theory is cluster decomposition, the principle that correlation functions factorize when operators are separated by large space-like distances. Imagine measuring the value of a field at one point in space and the value of another field at a point far away, so far that no signal traveling slower than light could connect them. Cluster decomposition says that, in the vacuum, these measurements are uncorrelated. The probability of seeing a particular combination of values is the product of the individual probabilities. There is no long-range order, no hidden connection between distant regions. Cluster decomposition ensures that the vacuum is featureless, that locality is respected, that the universe does not have mysterious correlations stretching across vast distances without any mediating interaction. Closely related is microcausality, the requirement that fields at space-like separated points commute or anticommute. If 2 points are space-like separated, meaning that no signal can travel from one to the other without exceeding the speed of light, then measuring the field at one point cannot affect the measurement at the other. Mathematically, this means the commutator or anticommutator of the fields vanishes. Microcausality prevents faster-than-light signaling, ensuring that the theory respects the causal structure of spacetime, that information flows forward in time within the light cone, never jumping across space-like gaps. The choice of commutator or anticommutator is not arbitrary. It is dictated by the spin statistics theorem, one of the deepest results in quantum field theory. The theorem states that particles with integer spin, bosons, must have fields that commute at space-like separation, while particles with half-integer spin, fermions, must have fields that anticommute. This connection between spin and statistics is not imposed by hand but emerges from the requirements of relativistic invariance, locality, and positivity of energy. It explains why electrons, which are spin 1/2 fermions, obey the Pauli exclusion principle, why no two electrons can occupy the same quantum state, while photons, which are spin 1 bosons, can pile up in the same state, leading to phenomena like lasers and Bose-Einstein condensation. Another profound symmetry, or rather a combination of symmetries, is enshrined in the PCT theorem. PCT stands for parity, charge conjugation, and time reversal. Parity flips space, turning left into right. Charge conjugation swaps particles with antiparticles, turning electrons into positrons. Time reversal runs time backward. Individually, these symmetries can be violated. The weak force violates parity. Certain rare decays violate charge conjugation and parity together. But the PCT theorem asserts that the combined operation of all three is a symmetry of any local, relativistic quantum field theory. If you flip space, swap particles and antiparticles, and reverse time, the laws of physics remain unchanged. The PCT theorem has profound consequences, including the equality of particle and antiparticle masses and the connection between the behavior of processes in the forward and backward time directions. Among the most surprising results in axiomatic quantum field theory is the Riche-Leader theorem. It states that if you take the vacuum and act on it with polynomials in fields smeared over any bounded spacetime region, no matter how small, the states you create form a dense subspace of the full Hilbert space. This means that, in principle, by manipulating fields in a tiny patch of spacetime, you can approximate any state in the entire theory, including states that describe particles excited arbitrarily far away. It sounds impossible, almost magical, but it is a rigorous consequence of the axioms. The Riche-Leader theorem reveals an extreme form of entanglement in the quantum field vacuum. The vacuum is not a simple, empty state but a deeply entangled web, where every region is correlated with every other. Local operations can reach across space, not by sending signals faster than light, but by accessing the correlations already present in the vacuum. However, creating states that differ significantly from the vacuum, states with particles far away, requires applying operators with large coefficients, which translates to unbounded energy. So while you can approximate distant excitations in principle, doing so in practice would require infinite energy, preserving causality and preventing paradoxes. The Hogg-Reuel theory, the Whiteman axioms, the Korlin-Learman representation, cluster decomposition, microcausality, the spin statistics theorem, the PCT theorem, the Riesz-Leader theorem. These are the pillars of the rigorous approach to quantum field theory, the results that emerge when you demand mathematical precision and logical consistency. They reveal a structure that is intricate and beautiful, where locality, causality, and quantum mechanics intertwine in subtle ways. They show that the vacuum is not nothing but a richly structured state, that particles and fields are not separate entities but aspects of a unified whole, that the laws of physics are constrained by deep symmetries and principles. In the quiet formalism of axioms and theorems, in the careful proofs and dense subspaces, the universe whispers its deepest truths, truths that are as much about mathematics as they are about matter, as much about logic as they are about light. In certain quantum field theories, there exists a symmetry called supersymmetry, or SUSY for short, which pairs every bosonic particle with a fermionic partner and every fermion with a boson. This symmetry, if it exists in nature, would be a profound extension of the known laws of physics, relating particles of different spins in a unified framework. Within supersymmetric quantum field theories, there is a special quantity called the Witten index, named after the physicist Edward Witten. The Witten index is defined as the difference between the number of bosonic and fermionic zero-energy ground states, states that have exactly zero energy in the quantum theory. If there are more bosonic ground states than fermionic ones, the index is positive. If fermions outnumber bosons, it is negative. If they are equal, the index vanishes. What makes the Witten index remarkable is its robustness. It is independent of temperature and coupling constants, meaning that you can change the strength of interactions or heat up the system, and the index remains the same. This stability is a consequence of supersymmetry, which protects the index from quantum corrections. The Witten index is a topological invariant, a number that depends only on the global structure of the theory, not on the details of the dynamics. Because of this robustness, the Witten index is useful for detecting spontaneous supersymmetry breaking, the phenomenon where the ground state of the theory does not respect the supersymmetry even though the equations of motion do. If the Witten index is non-zero, supersymmetry cannot be spontaneously broken, because there must be at least one state with zero energy that preserves the symmetry. If the index vanishes, supersymmetry might be broken, though the index alone cannot tell you for sure. In certain supersymmetric theories, particularly those called sigma models, where fields take values in some geometric space called the target space, the Witten index has a beautiful geometric interpretation. It equals the Euler characteristic of the target space, a number that counts the shape and topology of the space. The Euler characteristic is a fundamental invariant in geometry and topology, encoding information about the number of holes, handles, and other features of a surface or manifold. The connection between the Witten index and the Euler characteristic is a striking example of how quantum field theory and mathematics intertwine, how physical quantities have deep geometric meaning. Supersymmetry, beautiful as it is in theory, has not been observed in nature. No superpartners of known particles have been discovered in experiments. If supersymmetry exists, it must be broken, hidden at energy scales we have not yet reached. Physicists have developed ways to break supersymmetry explicitly while preserving some of its beneficial properties, particularly its ability to stabilize the masses of particles against quantum corrections. This is called soft supersymmetry breaking. Soft terms are added to the Lagrangian, terms that violate supersymmetry but are chosen carefully to be soft, meaning they do not reintroduce the problematic divergences that supersymmetry was meant to cure. These soft terms include masses for gauginos, the fermionic partners of gauge bosons, masses for scalar particles, and trilinear couplings, interactions involving three scalar fields. The key is that these terms preserve renormalizability, ensuring the theory remains predictive and calculable. In the minimal supersymmetric standard model, or MSSM, the supersymmetric extension of the standard model of particle physics, soft supersymmetry breaking terms play a crucial role. They generate the hierarchy between the electroweak scale, the energy scale of about 100 billion electron volts where the weak force operates, and the GUT scale, the Grand Unified Theory scale, which is many orders of magnitude higher, where the electromagnetic, weak, and strong forces might unify. Without supersymmetry, quantum corrections would drive the Higgs boson mass up to the highest scale in the theory, creating a fine-tuning problem. But the soft terms stabilize the Higgs mass against these quadratic divergences, keeping it at the electroweak scale without requiring unnatural cancellations. This is one of the main motivations for considering supersymmetry, even though it has not yet been seen. Within supersymmetric gauge theories, there is a remarkable exact result called the NSVZ beta function, named after Novikov, Schiffman, Weinstein, and Zakharov. The NSVZ beta function provides an exact relationship between the beta function of the gauge coupling, which describes how the coupling runs with energy, and the anomalous dimensions of matter fields, which describe how the fields scale. This exact result holds to all orders in perturbation theory and even includes certain non-perturbative effects. It is a powerful tool for understanding the dynamics of supersymmetric theories, for studying their renormalization group flows, and for identifying fixed points and phase transitions. Supersymmetry also has profound implications for solitons, stable, localized solutions to the field equations. In supersymmetric theories, certain monopoles, magnetic solitons, preserve a fraction of the supersymmetry. These are called BPS monopoles, named after Bogomolny, Prasad, and Sommerfeld. BPS monopoles saturate a mass bound, a relationship between their mass and their magnetic charge that follows from supersymmetry. Because they preserve some supersymmetry, BPS states are stable against small perturbations, and their masses can often be calculated exactly. The space of BPS monopole solutions, parameterized by their positions and internal orientations, forms a smooth geometric structure called a moduli space. The geometry of these moduli spaces encodes deep information about the quantum theory. One of the most celebrated achievements in supersymmetric field theory is Seeberg-Witten theory, developed by Nathan Seeberg and Edward Witten in the mid-1990s. Seeberg-Witten theory describes the low-energy dynamics of n equals 2 supersymmetric SU-2 gauge theory, a theory with extended supersymmetry and a non-abelian gauge group. The remarkable insight is that at low energies, the fundamental degrees of freedom are not the original quarks and gluons but magnetic monopoles and dions, particles that carry both electric and magnetic charge. Seeberg and Witten showed that the low-energy effective action can be determined exactly, encoded in a complex curve and a differential form. This exact solution revealed a rich structure of dualities and phase transitions, opening new avenues in the study of quantum field theory and inspiring developments in mathematics, particularly in the study of four-dimensional manifolds. Not all interesting phenomena in quantum field theory require supersymmetry. The Banks-Sachs fixed point is an example of a weakly coupled infrared fixed point in ordinary, non-supersymmetric gauge theories. Consider an SU, n_c, gauge theory with a number of fermion flavors, n_f, chosen carefully. If n_f is near but slightly below 3/2 times n_c, the beta function can have a zero at a small value of the coupling constant, creating a fixed point. At this fixed point, the theory is scale invariant, and it describes a conformal field theory at low energies. The Banks-Sachs fixed point is accessible in perturbation theory, making it a valuable laboratory for studying the renormalization group and the approach to conformality. Related ideas appear in theories called walking technicolor, which were proposed as alternatives to the Higgs mechanism for giving particles mass. In walking technicolor theories, the beta function is nearly flat over a wide range of energy scales, meaning the coupling constant runs very slowly. This slow running is called walking. When the coupling walks, the anomalous dimension of the mass operator, denoted gamma_m, can be close to 1, which enhances the suppression of flavor-changing neutral currents, unwanted processes that would otherwise be in conflict with experiments. Walking technicolor theories illustrate how the renormalization group flow, the behavior of couplings across scales, can have profound phenomenological consequences, shaping the predictions of theories and their compatibility with observation. The Witten index, soft supersymmetry breaking, the NSVZ beta function, BPS monopoles, Seeberg-Witten theory, the Banks-Sachs fixed point, walking technicolor. These are ideas at the frontier of quantum field theory, where symmetry, topology, and dynamics meet. They show that quantum field theory is not a closed chapter but an ongoing exploration, a landscape of possibilities where new structures and phenomena continue to be discovered. In the silent mathematics of indices and beta functions, in the smooth moduli spaces of solitons, in the slow walking of couplings across scales, the universe reveals its hidden order, its layers of symmetry and breaking, its deep and elegant simplicity beneath the apparent complexity. The journey through quantum fields is a journey without end, a path that leads always deeper, always toward new questions, new insights, new wonders waiting in the darkness. In the late 1990s, a profound discovery shook the foundations of theoretical physics. Juan Maldacena proposed a duality, a deep equivalence between two seemingly different kinds of theories. On one side was a quantum gravity theory, a theory that includes both quantum mechanics and Einstein's general relativity, formulated in a curved spacetime called de Sitter space, or ADS for short. De Sitter space is a solution to Einstein's equations with a negative cosmological constant, a universe that curves in a particular way, with a boundary at spatial infinity. On the other side was a conformal field theory, a quantum field theory without gravity, living on the boundary of that de Sitter space. The ADS-CFT correspondence, as it came to be called, posits that these two theories are completely equivalent, that every question you can ask in the gravity theory has an answer in the boundary conformal field theory, and vice versa. It is a holographic duality, a realization of the idea that the information contained in a volume of space can be fully encoded on its lower dimensional boundary, like a hologram that captures a three-dimensional image on a two-dimensional surface. This holographic principle had been suggested earlier by Gerard T. Hooft and Leonard Susskind in the context of black hole thermodynamics, where it was realized that the entropy of a black hole, the measure of its hidden information, is proportional not to its volume but to the area of its event horizon. The ADS-CFT correspondence gave this principle a concrete realization, a dictionary translating between bulk and boundary, between gravity and quantum field theory. It showed that space-time itself might be emergent, arising from the dynamics of a quantum field theory without gravity. The ADS-CFT duality has been more than a mathematical curiosity. It has been used to compute properties of strongly coupled systems, systems where interactions are so intense that perturbation theory fails. One remarkable application is to the quark-gluon plasma, a state of matter where quarks and gluons are no longer confined inside protons and neutrons but move freely, as they did in the first microseconds after the Big Bang. This plasma is created in heavy ion collisions at facilities like the Relativistic Heavy Ion Collider and the Large Hadron Collider, where gold or lead nuclei are smashed together at nearly the speed of light. The quark-gluon plasma behaves like a nearly perfect fluid, with very low viscosity, and calculating its properties from QCD is extraordinarily difficult because the coupling is strong. But using the ADS-CFT correspondence, physicists can map the problem to a dual gravity theory, where the plasma corresponds to a black hole in anti-de Sitter space. By studying the black hole, they can extract properties like viscosity and transport coefficients, gaining insights into the behavior of the real quark-gluon plasma. It is a striking example of how a theory of quantum gravity can illuminate the dynamics of matter in extreme conditions. Within the ADS-CFT framework, black holes in the bulk, in the anti-de Sitter gravity theory, correspond to thermal states in the dual boundary conformal field theory. A black hole has a temperature, the Hawking temperature, proportional to the strength of gravity near its horizon. In the dual CFT, this temperature is just the ordinary temperature of a thermal ensemble, a gas of particles in equilibrium. The black hole's entropy matches the thermal entropy of the CFT. The duality maps gravitational physics, with its horizons and singularities, onto the statistical mechanics of a quantum field theory, providing a new perspective on the nature of black holes and the information they contain. Perhaps most profoundly, ADS-CFT provides a non-perturbative definition of string theory, a candidate theory of quantum gravity that has resisted a complete, rigorous formulation. Through the duality, string theory in anti-de Sitter space is defined as the dual conformal field theory on the boundary. The CFT is well defined, at least in principle, and it encodes all the information about the string theory, including its quantum corrections, its non-perturbative effects, its full structure. ADS-CFT has become one of the most important tools in string theory, guiding research and revealing new dualities, new connections between different theories. Quantum field theory's reach extends far beyond high-energy physics and string theory. It provides powerful tools for describing low-dimensional and strongly correlated condensed matter systems, systems where electrons interact so intensely that traditional single-particle methods, which treat electrons as nearly independent, fail completely. In these systems, collective behavior dominates, and quantum field theory offers a language for describing emergent phenomena, phases of matter, and critical points. From high-temperature superconductors to quantum magnets to exotic topological phases, quantum field theory is indispensable. Returning to the realm of particle physics, one of the most successful applications of effective field theory is chiral perturbation theory, the low-energy effective theory of quantum chromodynamics. At low energies, far below the scale where quarks and gluons become visible, QCD is dominated by the lightest particles, the pions, which are the pseudo-Nambu-Goldstone bosons of the spontaneously broken chiral symmetry of the quark masses. Chiral perturbation theory expands physical quantities in powers of momentum and the pion mass, treating them as small compared to the scale of chiral symmetry breaking, about 1 billion electron volts. It is a systematic approximation, allowing precise predictions without solving QCD exactly. The leading order Lagrangian in chiral perturbation theory is the nonlinear sigma model for the chiral field, a mathematical object that represents the pions. This Lagrangian contains just a few parameters, determined by matching to experimental data, and it describes how pions interact at the lowest energies. It captures the essence of chiral symmetry and its spontaneous breaking, encoding Goldstone's theorem, which guarantees that the pions are light.